Okay, 9.1, identifying sequences. So here we are just talking about our sequences and what chapter 9 is going to kind of be based upon. On the left side, we have arithmetic. On the right side, we have geometric. So the first one, the arithmetic, it is a model using toothpicks. So if you can't really see what the toothpicks are, you can darken this. Basically, it is a box made with 2 toothpicks laid down on each side of it. So there's stage 1. We have here, we can count 1, 2, 3, 4, 5, 6, 7, total of 8 toothpicks making up stage 1. Stage 2, if you notice here, is the original 8 toothpicks laid down. But stage 2, we add some more toothpicks to it, kind of making a layer behind it, not including that corner right there. So if we are adding to it, we have an extra 1, 2, 3, 4, 5, 6 added to this. So on stage 2, did I say 6 or 1, 2, 3, 4, 5, 6, we have 14 toothpicks now laid down on there. Now following this same pattern, adding another set of toothpicks behind it, I want you all to pause the video and draw the next 2 stages below based on this pattern. All right, so check your work on here. If you notice, stage 3 had kind of, in a sense, 3 boxes here. So stage 4, I've got my 4 boxes, and stage 5, I've got 5 boxes now, each one being added on, not including that corner in the part there. So next it says, complete the table for the number of toothpicks used for each stage of the model up through stage 5. Stage 1 we already talked about had 8 toothpicks. Stage 2 we already talked about had 14. So if you notice here, the next one adding another set behind it would give us 20. And if you need to recount, stage 5 has 26 total, and stage 5 has a total of 32. Now we can find that easily, and I'm sure you've already noticed the pattern. Each stage here, we added 6 from the previous one to get the next amount. So if you had to recount, or you could just notice that pattern there, we could go on and find next stages after that by just adding 6 to the previous stage. So the next one says, use the following grid to make a graph of the data in the table. So here we have our stages, and we notice here on stage 1, we're just going to estimate the best we can because this isn't perfect, but stage 1 we had a total of 8. Stage 2 we had a total of 14. Stage 3 had 20, stage 4 had 26, and stage 5 had 32. Now, what do you think about this? Do you think our graph should be discrete or should it be continuous? I think this graph should be discrete because basically we are adding a new set of toothpicks for each stage. And we're not talking about what happens between the stages at all, adding even 1 toothpick. These are solid toothpicks, and we are adding 6 to each next one. It's not adding 1 each time or even adding a half of 1. So we added 6 toothpicks each stage. So not only can you not cut these in half, you also can't cut the amount in half. We can't do anything besides 6 each time. Now, what do you think of this graph? Do you think this is a linear function? This is a linear function. Basically, if you look at this pattern here, adding 6 each time, this is going up in a line. So the graph is a line. And you can specify a straight line, but really all lines are straight. All right, so let's go and look at the geometric now. For her electronic communications class, Keisha had been tasked with investigating the effects of social media. She decides to post a video in cyberspace to see if she can make it go viral. To get things started, Keisha emails the video link to 3 of her friends. In a message, she asks each of the recipients to forward the link to each of her friends. Whenever a recipient forwards the link, Keisha asks him or her to attach the following message. After watching, please forward this video link to 3 of your friends who have not yet received it. Who has gotten one of these messages before? These are very typical. We've seen these before. We've seen them in Facebook. We've seen them through, they used to be called chain emails. But basically, to visualize this, we have a tree diagram. So it shows all the possible outcomes of the event. So if we look at this first one here, we have Keisha, top stage 1. She is the first one who has this video, and it tells us that she sends it out to 3 of her friends. Now, each of those friends send that link that says to send it to 3 of their friends. So 3 of their friends watch it, 3 of their friends watch it, and 3 of their friends watch it. So let's talk about these stages, and let's talk about how this can be related to this chart. Assume that everyone who receives the video link watches it and sends it on. So this is the number of people who have now watched the video. At stage 1, Keisha is the only person who has watched this video. At stage 2, 3 more people have watched the video at that stage. We're not talking cumulative here. We're just talking about the number of people who have watched it at that stage. So stage 2, her 3 friends watch that video. Now after stage 2, they send it on, and we have 3 friends from each of those friends who are watching this video. So now we have 9 people who are watching that video on that stage. What would be the next amount? All right, if you said 27, you would be correct, because each of those 9 people sent it to 3 of their friends, and if you have 9 people send it to 3 people, you have 27 people now watching this video. Okay, so let's get to graphing this one. Stage 1, estimate best you can, we have 1 person watching it. This is 5, so 1 would be like way down here. Stage 2, notice the jump here. We've got 3 people watching it. Remember, that first tick mark is 5, so it's not quite there yet. Stage 3, we have now 9 people, so right below 10. And stage 4, we have 27 people watching it. So this is 25, 27 would be approximately right there. Now, what do we think about this one? Would it be continuous or would it be discrete? I would say discrete on this one as well, because we're talking about in between, there's nothing happening in between these stages. So no stage in between. And basically, each time, 3 people are watching it. Each time, 3 people watching. Okay, so what do we think about this? Is this a linear function? No, I hope you said no to that. This is not a line. Your thing is, if you notice here, it's kind of making a nice little curve right here. So no, and we can say a couple things. The graph is a curve, plus you can notice last time we had +6, +6, +6. We don't have a constant rate of change this time. It's not going up by a constant amount. So I'm going to say no constant rate of change. Like I said, also you can say that this graph is a curve. All right, flip it over to the back side of notes. Now we got some definitions, basically what this puts us all in perspective. An ordered list of numbers is called a sequence. Now hopefully you've actually seen some things about sequences in general. Sequences is basically just a pattern. So we're going to notice some patterns going on here. The numbers in a sequence are called terms. Between our arithmetic and our geometric, we've got a big difference here. We noticed from that first part that one of them was linear and the other one was not. So our arithmetic is a sequence in which the difference between consecutive terms, consecutive just means one term after another, so the difference between consecutive terms is constant. So let's talk about using what this difference is. We call it a common difference because it's the same each time. So we always denote this, so denoted by the letter D. And we're going to kind of look at a sequence right here. We've got 1, 3, 5, 7, ... meaning it can keep going on forever. And we can find this common difference two ways. You can first of all just see what's happening in the pattern. Going forward, we have here going from 1 to 3, 3 to 5, 5 to 7. We notice each time it is increasing by 2. Another way, if you have like negative numbers or if it's just hard to find the sequence, you can also subtract backwards. So you go to the last number in your sequence and subtract, so like 7 minus 5 equals positive 2. So these two numbers here, if you notice the pattern or if you have to actually subtract backwards to find that pattern, that is going to be the same number. Now, some of you might already notice from the front side in the graph, the common difference is the same as the slope in these. It's kind of like linear, oh, this is the slope, this is what it's going up by each time. So for this one, I'm going to say common difference, D equals, and this one is a positive 2. Now our geometric, we have our geometric sequences now. Let me set it over here. A geometric sequence in which a non-zero constant ratio exists between consecutive terms. So before we had a common difference, now we have a constant ratio, which we call the common ratio. The reason it cannot be 0 is because if it were 0, you would not have a sequence that went up by a certain amount. So this one, common ratio, is denoted by an R. So if we notice here, I'm going to give you a sequence that's geometric. 2, 4, 6, oops, my bad, 2, 4, 8, 16, ... Now, two ways you can do this one as well. You can first of all just notice the pattern. So going forward here from 2 to 4, from 4 to 8, and from 8 to 16, we notice we are multiplying each time by 2. Or if it's like fractions or if it's negative numbers, you just can't not find it. Just like before when we subtracted backwards for the difference, ratio is the same as division. We can divide backwards. So I'm going to go here and I'm going to go 16 divided by 8, and that gives me a positive 2. 8 divided by 4, 4 divided by 2. Every time I get that positive 2, because I'm trying to find what number is multiplied to the next. So here, my ratio, R, equals positive 2. All right, so let's do some practice problems now. All we are doing in this lesson is we are identifying it as arithmetic, geometric, or maybe it's neither. Maybe it actually has no pattern, even though it looks like it has a pattern, but it's not actually either one of these sequences. If it's arithmetic, we're going to state the common difference. If it's geometric, we're going to state the common ratio. So this first one, we have 5, 8, 11, 14. What do we think about that one? All right, so a couple of things we can do here if you have not noticed it already. The best way to find it is by doing both of these things, subtract backwards and divide backwards. If I first start with subtracting, 14 minus 11, I get positive 3. 11 minus 8, positive 3. 8 minus 5, positive 3. Well, if I just subtracted backwards and got the same number each time from subtracting, that is my arithmetic. So this sequence is arithmetic, and my common difference each time added 3 to get to the next problem, so positive 3. All right, so number 2. What do we think here? 1, 4, 9, 16. Well, if I subtract right here, 16 minus 9, I get 7. 9 minus 4, I get 5. So we're not finding a common difference. So I'm going to move on to my division. 16 divided by 9 gives me like 1.77 repeating. 9 divided by 4 gives me like 2.25. So I know this is not getting the same number division-wise. Now you're probably seeing a little pattern to this. Maybe 1 squared, 2 squared, 3 squared, 4 squared. That's great. It does have a pattern. However, it's not arithmetic or geometric because does not have a common difference and it does not have a common ratio. Even though if you find a pattern, it does not mean it's one of our types. Okay, and number 3. 64, 16, 4, and 1. Well, if I subtract, 1 minus 4 is negative 3. 4 minus 16 is negative 12. So I'm not finding a common difference. What about if I divide backwards? 1 divided by 4 is 1/4 or 0.25. 4 divided by 16, simplifies to 1/4. 16 divided by 64 simplifies to 1/4. So here we have our geometric and our common our common ratio is 1/4. Now, that means you have to find the number of how this is changing. So if I go forward from 64 up to 16, I understand that you are dividing by 4, but I need to know exactly multiplication, every time it's multiplication of what's happening to get to each number. So I'm actually multiplying by 1/4. You cannot say, oh, my ratio is 4 because it's dividing by 4. No, you have to find what number is being multiplied forward each time, just like you have to find what number it's going up by each time. All right, I'm going to let you do some practice on your own. Write down number 4, and then I want you to pause the video. Number 4 is 7, 9, 12, 15, ... All right, go for it. Pause the video. All right, this one's neither. If you went to subtraction, you found it went up, this one went up by 3 each time, this one went up by 3 each time, but this one only increased by 2. If you went through and did your division, this one divided to 1.25, this one divided to like 1.333, so this is neither geometric or arithmetic. All right, here's number 5. 14, 7, 0, negative 7, ... Pause the video and determine what type it is. All right, this one's arithmetic. This one is actually decreasing by 7 each time. So first I subtracted backwards and I found negative 7 each time, but you can also figure out from 14 to 7, it decreases by 7. From 7 to 0 and 0 to negative 7, it's every time it's decreasing by 7, so my common difference is negative 7. All right, number 6, your sequence is 1, negative 3, 9, negative 27, ... Pause the video and figure it out. All right, this one's geometric. Each time when I looked back and I did my division to find my ratio, negative 27 divided by 9, I got negative 3. 9 divided by negative 3, negative 3. Or, looking at it forwards, how did it go from 1 to negative 3? From negative 3 to positive 9. From positive 9 to negative 27, well, each time it was being multiplied by a negative 3, so my ratio is negative 3. All right, the last section of notes here. What you are doing on this section is you are creating a table. So let's talk about this first one together. We notice on the first example, our stages, we had like stage 1, stage 2, stage 3. There's no stage 0. There's actually technically no y-intercept for these. So that's the first thing I want to talk about. This first problem, this first number in our sequence, when I make my table, so these will be, X will be my actual position. It's kind of like those stages on the front. So the position. Position would be the first number of the sequence, the second number of the sequence. So these are actually the position of each term, because those are the numbers in the sequence. So position 1, position 2, I have 1, 2, 3, 4, 5 numbers. 1, 2, 3, 4, 5, and it could keep going because I have ... Now your y values is the actual terms in the sequence. So the first term in the sequence is positive 2, second term in the sequence is 2.5, then I had 3, then 3.5, then positive 4. So there's our terms in the sequence. Now, next thing we're going to do after we get our table is we're going to graph this. So let's draw little axes here. Here's my x. Here's my y. I'm going to count my position. This I'm going to label it. It's position. Going up by 1 each time. And then our terms will be here. Since these are going up by a half each time, I'm going to kind of count this as 0.5, meaning this is 1, skip 1, this is 2, skip 1, this is 3, skip 1. That top one is labeled 4. Let me do different colors so you can see that 4. All right, so our first one, first position, is on positive 2. Second position is 2.5. Third position is on 3. Then we head on 3.5 and positive 4, position 5. We notice here that this is what type of sequence? Arithmetic. It is going up by a positive 5 each time. That's our common difference. And last thing I'm going to do is I'm going to list my domain and range. Notice though, once again, just like our examples from the front side, these are discrete functions because nothing's happening in the middle of the positions. It is literally from one position to another. All of these will be discrete. So my domain, or my x values, I'm going to list off as a roster. First position, second, third, fourth, fifth. Now keep in mind, these can keep going. Since these did go up by 1 each time, I also could have done it like x is an element of, well, technically whole numbers, but these are all natural. So I can do natural such that x is greater than or equal to 1. That would be another way to write that domain, showing it keeps on going. My range, however, skips values. So I have to list it off as a roster, 2, 2.5, 3, 3.5, 4, comma, dot, dot, dots. All right, let's go ahead and do the same thing with example 2. Pause the video, check your work in just a moment. All right, once you get your graph done, you notice that this one is not linear. This is our geometric sequence. It is being multiplied by a factor of 2. My domain, I put this time in the natural is greater than or equal to 1, or you can do the same domain from this previous one as roster. And my second one here, listed off as roster notation because it skips values. All right, that is it for your introduction for 9.1. Be ready for that next section tomorrow.